We're going to be talking a little bit about exponential functions. I have listed a few of the important exponent rules. I think these should look familiar. You've probably done them many times in the past. The first one is that if you have the same base and two things are being multiplied, you add their exponents. The second one is a power to a power, means that you multiply the exponents. The third one, this actually applies for any exponent, not just two. But basically, if you have two things being divided, you are going to distribute the exponent that's outside of a parenthesis. This also works if you have two things being multiplied, like this. Like if we had a second on the outside, that'd be x squared times y squared. However, I do want to point out that if you had something like this, that is not going to be x squared plus y squared. So the exponent doesn't distribute that way for addition or subtraction. In this case, you would have to use the FOIL method. The fourth one, you have a power to 0. That's going to be equal to 1. The only exception for that one is if x is not equal to 0. That doesn't come up that often. You might see that at some point in calculus in the future. And the fifth one is if you have a negative exponent, we take the reciprocal of it and change the exponent to positive. And fractional exponents give you roots. So if there's any of these that you feel like you need more practice with, please let me know. You'll have a little bit of practice embedded in the class, but we're not going to be doing lots of problems specifically for these rules. I'm kind of assuming that you've done these in the past. So an exponential function is a function that is of this form right here. And in that equation, that letter C is called my initial value. The reason I call that the initial value is because if you were to set x equal to 0, you would actually get C as your answer, because you would have a exponent of 0, so it would be C times 1. So that's my initial value. My A is called my growth factor. And actually the X usually is, not always, but usually is going to represent time. So we'll do a few graphs of these. The first one I have is f of x is equal to 3 to the x power. For this one, my base is greater than 1, and in that case, we're going to call that exponential growth. And the second equation I have, f of x equals 1/3 x. If your base is between 0 and 1, that's called exponential decay. So we're not going to do anything with those quite yet, but we will pretty soon. So just keep those ideas at the back of your mind, growth and decay. So for f of x equals 3 to the x power, easiest way to graph this is most likely to make an XY table. I'd like you to maybe pause the video, try it on your own. So if you choose, my recommendation whenever you're graphing something is to choose some negatives, choose some positives, and then go from there. So you'll notice that my negative values are going to give me really, really small fractions. And then my positive values, actually, if you were to go like choose 3, it would get really big. So this one grows very, very quickly. So you'll notice I only drew half of my graph because I want to point out a few things. First of all, by the way, that value at 2 should be 2, 9. I didn't quite go through all the points. Keep in mind I'm using my finger, so my graph's not going to be perfect. So on the right-hand side, I want you to notice that it goes up very, very rapidly. Like I said, even if I start with x equals 3, it's going to go up really, really high, really, really quickly. So it goes way off the graph. That's what exponential growth tends to do. Now, if I get a very negative number, it's going to give me a y value that's really small, But no matter what negative value you get, you never are going to, that you use for x, you're never going to get a negative y. You're actually never even going to get to 0. So your left-hand side is going to get closer and closer to 0, but it's never actually going to touch it at 0. There is a horizontal asymptote at y equals 0 on this one. So please just keep that in mind. Exponential functions do have horizontal asymptotes. If there's no shift, like there's nothing being subtracted at the end of it, it's going to be at 0. So I also want to point out that even though this graph looks like there might be a vertical asymptote somewhere, there is not a vertical asymptote anywhere. There's not one at 3, there's not one at 4, there is no vertical asymptote. No matter what value you put in for x, you will have a y value on this. So I'll write my domain is going to be all real numbers. My range is going to be all values of y, such that y is greater than 0. Okay, so for my next one, by the way, notice that I put greater than, I did not put greater than or equal to. Next one, you can do the same thing. I'd like you to use the same numbers, try to make an XY table on your own. So keep in mind that if you have a negative exponent, I'll actually do the first one for you. I'm going to use another color because I think this one's a little harder to see. If you have a exponent of -2, just remember that that is, there's a few ways to do this problem. I don't really care how you do it. What I tend to do is if I have a fraction to a negative exponent, I flip my fraction, make that exponent positive, and it gives me 9. So whatever way works best for you is fine with me. You might have other ways that you want to do it. If you have no way to do this, you're not sure how to do this at all, let me know individually. I can help you out. So you will find that you get actually the same values that you had for the previous one, but they're going to go in the opposite order. And this one should be 1/3, by the way. So for this one, when I draw my graph, it looks like the same one that I had on the other side, except it goes backwards. And if you are really, really observant, you might realize that this function right here is actually the exact same function as f of x equals 3 to the negative x. So those are the same thing. That's why the two functions are reflections of each other, because they're the same thing. It's just that there is a reflection over the y-axis. So I do also want you to notice that exponential growth, as it goes to the right, it grows a lot. Exponential decay, as it goes to the right, it gets smaller and smaller and smaller. This has the same domain and range as the previous one. So there is a single horizontal asymptote, and it's at y equals 0, just like the previous one. So we have a really important irrational number that's called E. It's actually named after the mathematician Euler. That's why they use the letter E. It's equal to approximately 2.71828. It's a number that just keeps going on forever and ever. If you want to, you're welcome to put e times 1 into your calculator, and so you could see what it looks like, or e to the 1 in your calculator so you can see the whole thing. Or you can go online and find many, many digits. We're just going to think about it as 2.718. That's as far as we're going to worry about here. So the number e ends up being used a lot in growth functions. It is really one of those useful things that you'll see next year in calculus. You use it a lot. I'm not going to go into too much detail about like the history of it, but there is a lot of history of it. What I would like to talk about, though, is, first of all, the graph of E. Now, the same thing as our previous problem, it actually is going to have the same shape as the stuff that you had previously. The only difference is just the values that it's going to touch. So for E, if you do an XY table, when I do negative values, those are really hard to get without a calculator. If you want to use a calculator, that's fine. If I do x equals 0 for this, I will get 1. If I do x equals 1, I will get E, which is about 2.718. These are actually I want you to know the shape, and I want you to know that these 2 points are on this equation, on this graph. You don't really need to know much other than that. But I also want you to know that it's like every other exponential function. It will have a y-intercept of 1. You'll find that all exponential functions have a y-intercept of 1. The other thing is that it grows really, really quickly, and it has an asymptote at y equals 0. So it's really similar to all other exponential functions, but it just uses the letter E instead of a numerical base. We're going to solve a few exponential equations. I'm going to tell you right now there are several ways to solve these, but I'm going to show you the way to do it without what we're doing, the thing we're doing in the future, logarithms. So for this one, I have 4 to the 2x minus 1 is equal to 8 to the x. It's important that you notice that these are 4 and 8 are both powers of 2. What we can actually do is we can rewrite those so that we have the same base. So that's the only way that you can really do that. Now, if these weren't powers of 2, you wouldn't be able to rewrite them with the same base, but in this case we can. So we know that 4 is the same as 2 to the second power. So I'm going to rewrite 4 as 2 to the second. I keep my outside exponent the same for now. 8 is the same as 2 to the third. So again, I'm going to rewrite my 8 as 2 to the third. I keep the x on this outside the same for now. The next thing I'm going to do is rewrite it again. I keep my 2 as my base. I'm going to start with the one on the right because it's easier. So 2 to the third to the x power, we have an exponent property that says if you have a power to a power, you multiply your exponents. So that's going to be 3x. Same thing happens on the left side. I'm going to do 2 times 2x minus 1. I want to warn you that you can't just multiply the 2 times 2x. You actually have to also multiply the minus 1. You have to use the distributive property. So I end up getting 2 to the 4x minus 2 is equal to 2 to the 3x. Now what I'm allowed to do, this is a fun trick. I can rewrite this as 4x minus 2 is equal to 3x. And then I can solve it out. I get negative 2 equals negative x. So my answer for this one is x equals 2. And I do recommend that you go back and you check your answer. I think that's a good idea. So we're going to check. When we check our answer, we get 4 to the 2 times 2 minus 1 is equal to 8 to the second power. On the left side, I get 4 to the third power is equal to 8 to the second. 4 to the third, we know, hopefully we know, is 64. 8 squared is also 64, so it does check out. So this problem is actually really similar to the previous one. We need to get two things equal to each other that have the same base. This time, however, we have a bunch of e's. So this is where our knowledge of properties of exponents is going to be really useful for us. So the left-hand side, I can't actually simplify anything, so I'm going to leave it as is. The right-hand side, however, I can simplify some stuff. So first of all, I have e to the x to the second. Keep in mind that that is the same as e to the 2 times x. My next thing, I have 1 over e to the third. that can be rewritten as e to the negative third power. The last thing I'm going to do on that right side is add my exponents. Keep in mind we have the same base, so we're allowed to add our exponents. 2x plus negative 3 ends up being the same as 2x minus 3. Now I can actually do what I did on the previous one. I can set my exponents equal to each other and solve. When I set my exponents equal to each other, I end up getting x squared plus 2x minus 3 is equal to 0. I'm going to go ahead and factor. I get x plus 3 times x minus 1. That gives me x equals negative 3 and x equals positive 1. You're welcome to go back and check this. If you check it, you can substitute in the two values for x. You will find once you use a bunch of properties of exponents that you do end up getting a equivalent statement.